All right, welcome everyone. It's 10:10 on Wednesday. I hope everyone's having a good week. I'm going to begin the lecture for today. Just a brief comment. If you can't hear me, just let me know. Chime in, please. And if you can't read anything I write or project, just let me know. I'd appreciate that. Thanks. Okay, so there will be weekly discussions for this course, as I mentioned on the first day of class. And there's an announcement on our Canvas website, and I think the TA, Avi, has sent out an email to everyone. And we've actually decided to have just two sessions for now, okay? And these sessions will run from 11:30 to 12:30 and from 5 to 6 on Wednesdays, okay? And these are Zoom sessions, and the link is the same as you use for our Monday, Wednesday, Friday lectures at 10 a.m. So all you have to do is click on the link, and you can find the link in the email that was sent, or by going to this announcement titled Chem 443 Weekly Discussions on the Canvas website. And at the bottom, you'll see the Zoom link. You can access the sessions however you wish to do so. Okay, any questions on that? Okay, and are people following with the homeworks and the readings? Any questions there? Feel free to chime in, unmute yourself if there's any issues. Okay, the other thing I want to mention, via the Canvas website for this course, if you go on the left where you have all these tabs, there's something called modules. If you click on the modules, you'll see various sections. One section is the lectures, where I will put things in the future. There's also this section called useful thermodynamic resources, and I've listed a few things here. I would encourage you and invite you to, at this point in the course, go through this ideal gas law practice problems 1, 2, and this bit of a write-up on equations of state. I introduced the notion of an equation of state last class using the ideal gas law as an example. And so I would encourage you all to take a look at these as well at this point in the course. So these two should be fairly simple for you. They're ideal gas law problems, fairly basic. They'll get you used to thinking about the ideal gas law and the relationship between the equation of state variables, PVT, that we discussed last class. And then equations of state is a more formal discussion of some of the ideas behind equations of state. And it's something that's useful just to be exposed to. So I put it up there as an extra useful resource. Okay, moving on. Again, if you have any questions and need to interrupt, please unmute yourself, and we'll go with that route using voice. That way you don't have to worry about things. Last class I mentioned there was a question about whether pressure is intensive or extensive, and we agreed that pressure is an intensive property. It doesn't depend on how much material you have. And I alluded to the fact that actually you can describe relationships between pressure, volume, and temperature, where volume actually is an extensive property, but pressure and temperature are intensive in a three-dimensional manner. And I've shown a picture here. I posted this on the Canvas website under the modules, under extra resources. And this is actually what it looks like. This three-dimensional representation of pressure, volume, and temperature for a single component. Okay, and so on this axis you have pressure, on this axis you have volume, and on this axis you have temperature. And you can see, in fact, that it's a very rich and complex surface in 3 dimensions just for a single component, a single material. So water, this would not be representative of water, and we'll see why a little later. It has to do with the slope of this line, the solid liquid equilibrium. But you can see that it's actually a rather interesting and very complex 3-dimensional structure. And so what you've been introduced to in terms of pressure temperature diagrams, you may have been told that those are phase diagrams. Pressure temperature diagrams where you have pressure on the y-axis and temperature on the x-axis, for instance, actually are a projection of this three-dimensional surface where the volume essentially has been collapsed. And so when you look at a pressure temperature phase diagram, what you're doing is looking at it from this direction towards the surface. So all you see is the pressure and the temperature, and the volume essentially has been compressed, so you don't see it. So you don't see some of the more nuanced features of the phase diagram, but you get a basic idea of the solid liquid vapor phases and their coexistence regimes, the lines or the curves. Okay, so you take a look at it, think about it, and we'll revisit this later. Any questions? Okay, awesome. So I'm going to move on to, I'm going to share a different, I'm going to share my iPad now. Let's see if that goes through. It always happens. Okay, can everyone see the screen with the iPad? Okay, it should have should say types of system properties at the top. Okay, and here I want to sort of just address one more thing in terms of this idea of extensive and intensive. A student made the suggestion that pressure is extensive because if we use the ideal gas equation of state and transform it to obtain this expression for the pressure, the comment is, well, pressure depends on N, and so perhaps it is extensive. An easy way to realize that it isn't is that N over V, these two guys can be taken out times RT, but we know what N over V is. This is just another way of saying density rho. And so that's just equal to rho RT. This is the Greek letter rho, RHO. Okay, and we know that density is intensive. So in fact, pressure is dependent on this intensive property. Temperature we know is intensive. It doesn't depend on the amount of material you have, and R is just a constant. So therefore, pressure is indeed an intensive property. Okay. The other way to think about why pressure is intensive, well, if you look at phase diagrams, there is no axis that represents N. So regardless of how much N you have, this phase diagram doesn't change. You can have 100 moles of water or you can have 500 moles of water. The pressure, the phase diagram will not change, and hence pressure and temperature for a system at equilibrium are intensive indeed. Okay, all right, so I think I've belabored that point enough. If there are any other questions, please let me know. Okay, let's move on. So last class we were talking about work, and work is a very general concept. It's one of the ways systems interact with their surroundings. The other would be heat. Okay, and so we're going to look at heat as well. So first we'll characterize and quantify how we're going to treat work through mathematical models in this portion of the course. And we're going to assume that delta N is 0 for this case. So we're looking at a closed system. Okay, so this is a closed system for now. For now, we'll let this constraint relax later on, because of course we know that chemical reactions involve delta N not equal to 0. And as chemists, we want to treat systems where delta N is not equal to 0. Okay, and the type of work we're going to discuss is pressure volume work. And so the system that we created or set up was this idealized piston cylinder system where you have a gas and it's at equilibrium initially. And these are the variables that characterize this equilibrium. We can say that there's a certain number of moles, but of course, N is not going to change. The number of moles will not change. So we can either opt to choose N to be here or not. Okay, so the moles don't change in this this example. And here, this piston is exerting an external pressure on the gas. Okay. This is massless piston head, so we don't have to worry about any force that's exerted by the actual mechanical things in the system. It's just there's some abstract system. Perhaps it's a pump far away. We don't know. It could be a pump or any other mechanical device, which we don't really have to worry about at the moment, that exerts an external pressure on the gas. It could even be the atmosphere that's exerting an external pressure. So I want to impress upon everyone that there's a pressure that would be involved with the equilibrium state of the gas, okay? So let's just say that out here we have atmosphere, okay, outside of this piston cylinder assembly. So we have gas as our system. That's what's denoted by the red. And in this region, it's just the atmosphere. This piston assembly is sitting out somewhere outside, okay? If we wait long enough, this piston head and the assembly is not going to move. It's just going to stay in some stationary position Z. Okay? So that's at equilibrium. And what that means is that if you're given a particular temperature, okay, there could be a particular temperature outdoors, and a particular volume of this gas that it's going to take on with a given number of moles, you will find that the internal pressure, the pressure that the gas exerts on the walls of the piston, this wall, this wall, this wall, and this wall, is going to exactly equal whatever the external pressure is. In this case, it would be atmospheric pressure because we're just letting it sit outside under the atmosphere. Okay? Is that clear? And so at that point, the internal pressure, or the pressure that the gas would like to be under at these conditions of temperature, volume, and number of moles, but again, pressure doesn't depend on N in a closed system, would equal the external atmospheric pressure. Okay. Now, what happens is we can actually control this external pressure, and that's why we have to label this guy as external. We can't just label it P, because there's going to be a difference between the pressure that the gas feels at any moment and the pressure outside of our system as defined by the gas. Okay, so it's sort of like you being outside, sitting on the lawn at UD, right, under the atmosphere, and just lie down there for a little while and let yourself equilibrate, and you'll see that the pressures, you're not moving. There's nothing, whatever pressure that the atmosphere exerts on you, you exert back, and so now you're at equilibrium. Okay. This external pressure is unique, or it's different from that which is the equilibrium pressure or the internal pressure of the gas, in that we can essentially change this external pressure as quickly as we want. Okay, so now if this gas piston cylinder is sitting outside, it's at equilibrium, nothing is changing, and this piston head is stationary, we can come along and one of you could just press down on this piston head, right? And you can either press down on it very quickly, almost like a step change. You can just come there and, you know, jump on it, or you can press on it slowly, right? And compress the gas. So this action would lead to compression of the gas. Okay. During that process, there would be a lot of things that are changing in this cylinder, in which case there would always be a difference in the pressures between the external applied pressure and what the gas feels during that process. Okay, they would not necessarily be equal. And in fact, if this guy is moving, if the piston head is moving, the two pressures would not be equal, right? Because if you have equilibrium, the pressure in the gas, which is your system, would equal the pressure outside of the gas. If the two pressures are not equal, this guy is going to be moving. The piston head is going to be moving. Okay, so that's why we have to label this guy as P external. Is that clear? Because there will always be a difference between the external pressure and the internal pressure, or the equilibrium pressure of the gas, when you have a process occurring. And that process is defined by a change in the volume for the moment. Okay, is everyone clear with that? Please chime in if that was not clear. And so that addresses the point of labeling this pressure as external. Okay, so we discussed all of the setup for the gas cylinder here. I'm not going to go through it. Just to note that it is an idealization. Our system is the gas. And we saw that the question that we posed is what amount of work is involved when we compress the gas, in this example, from some initial volume V1 to a final volume V2. And this volume change, delta V, which is defined as V2 minus V1, is made possible by having this external pressure change the Z position of this piston head from Z1 to Z2, where Z2 is lower than Z1. So you see here that we had motion of this piston head downwards to decrease the volume, okay? So we went through a discussion of work from the physics definition, which is the only definition. And this is the definition for an infinitesimal amount of work that's associated with an infinitesimal change in the height of the piston head. And when you have an infinitesimal change in the height of the piston head, that corresponds to an infinitesimal change in the volume of the gas, okay? So it's all consistent. We're talking about very, very, very small changes. Now, we saw that these were vectors. The force is a vector, and a change in the position of this piston head, since position actually is a three-dimensional vector, they're both vectors. We take the dot product or the scalar product of these two vectors, and we see that it turns out to be a scalar result. And of course, work has to be scalar because just from our intuitive understanding of work, there's no direction to work, okay? Work is just work. It's some amount. There's no directionality to it. And so the scalar product takes care of converting vectors into scalars. And in this case, since we only have motion in Z dimension, in the Z direction, we don't have to worry about forces that change the position of the piston head in the X and Y direction. So there's only force in the Z direction. So the direction of the force leads to motion in that direction. So in this case, we only have motion in the Z direction, so we only have Z force. And so our expression for the work boiled down to this. So this is the differential amount, or the infinitesimal amount of work that's associated with an infinitesimal change in the Z position of the piston head, and that's labeled as dZ. Okay? And Fz is the force in the Z direction. An assumption in this discussion is that Fz remains constant over this infinitesimal change in Z position. Okay? Whether this piston head changes really, really rapidly or very, very, very slowly, the assumption here is that the force during this very small change in Z of the piston head is constant. And actually, it's not a grossly poor approximation. It's actually a rather good approximation. Okay, we don't have to worry about this. It's a good approximation. Okay, so now we know what dz is. We have an intuitive grasp of that. What's fz? Let's sort of consider fz. Okay, so f of z, that's the force in the z direction. Okay, as we move this piston head. Okay, so this piston head is moving down, and because it's moving, there has to be a force. Okay, otherwise, it wouldn't be moving. And we can relate this force to the only thing that's acting in that direction, in the z direction. That's this external pressure. Okay. So since this piston head is moving downwards in the z direction due to a force, and since the only thing in our setup that's acting downwards is this external pressure, we have to relate this force to the external pressure. And so that's what we're going to do now. How do we relate F of z to force, or sorry, pressure? Fz must be related to P external. Okay, how is this? How? Well, we know that P external, from the definition of what pressure is, if you look at the units, is force per unit area. So P external is some external force, and I'll just let that external force be force per unit area. Okay. And I remind you that the piston head has cross-sectional area equal to A. And that was just up here. I hope I still have it. Yes, right here. Okay, so A is the cross-sectional area of the piston head. So if we want to know what this force is, okay, we can just rearrange this expression. Okay, so we just isolate force. Force is equal to P external times the cross-sectional area. That's all we need to know. Okay, so now we have our force. And this force is equal to Fz, because that's the only, that external pressure is the only source of force that moves this thing, right? That's the only thing in our picture up above. That's equal to F of Z. So I just bring these two guys down again. That's just going to be P external, EXTER and AL times the cross-sectional area. Okay. Now, what is the cross-sectional area? Well, we don't know. We don't have to know that. Okay. So now let's go back and finish our expression for work. Okay. Now we know what F of Z is. We just computed it right here. F of Z is this guy. So back to work. dW, and I remind you that I use this little line here, okay, and we'll get to that in a moment. So dW, which is Fz dz, dz, right that here, is going to be equal to, now we substitute in this guy for F of Z, okay? And so F of Z dz becomes P external times the cross-sectional area, and then we still have our dz left. Okay, and that's dw. So that's pretty cool, because now what we've done is we've obtained an expression for this infinitesimal or differential change in work as this piston moves in terms of a parameter or this control knob that's in our system setup, and that control knob is this external pressure. Okay, so that's good because this is something that we can control, and so that's good. It gives us a handle. It allows us some control, and that's good. That's what we want. It's no longer a general thing, but it's now becoming more specific. Okay, the other thing I want to think about here is this A dot dz. Okay, we can actually simplify this. What is A dz? Well, if we think about it, A is a constant, by the way. That's the cross-sectional area. Again, I remind you. So it's constant. Okay, so here's our piston, right? So it starts in this position. It has a cross-sectional area A. Okay, and then finally, I'm going to make this a little bit thinner, but you can imagine that it's the same system. So again, A is constant. A doesn't change, but what has changed is the Z position of the piston head, and that Z position, that change in the Z position is given by this double arrow. Okay, approximately. I mean, you can see that the change in Z is this guy, right? It's not. It's obvious, and so that's what we're going to label dz. Okay, but A dz, right, is just going to equal dv, where V equals volume. And so AdZ is the infinitesimal change in volume due to exerting external pressure on our system, which is equal to the gas. So it's quite nice that A dz is really just the differential or infinitesimal change in volume, dV. Okay, any questions or comments at this point? Please chime in, unmute yourself and ask a question if you need to. Okay, so I will continue. So what that allows us to write then, dW, again, I bring down this little line, is equal to Fz dz, and now we'll just write everything, which is P external times dz, which we, times A, sorry, I left out the A, P external A dz, okay? Now just carry down the dW again, but the A dz is just dV. So this is just P external times dV. But this is great because now we've gotten an expression for the work, the differential amount of work done when our system changes or undergoes this process, right, in terms of these control variables or these control knobs, pressure and volume, that are very specific to the system. Okay, so we started with a very general dW is equal to sorry, let me go back. F dot dr. So this was very general. Actually, it was the most general. Okay, and then we did some manipulations, taking into account the nature of our system, and we came to a very specific expression for the work, and that's this guy. Okay, so I hope that this is instructive in terms of how we start with something very general, and then once we define something specific, and that something specific is always something that deals or has to deal with the problem that you're dealing with. Your problem is very specific, right? But somehow we can start always with a general approach, and using our logic and analytical thinking, boil it down to something that is very specific for our particular system. Okay? And so that's how the general logic works in terms of beginning with physical principles and here is the application of the physical principle to a specific case. Okay, and so that is how this unfolds. That's how the story unfolds. Okay, now we have to have a convention. Okay, so let's accept this. Again, any questions, comments? I really want everyone to be clear on this. Okay, great. We have a sign convention. And by sign, I mean S-I-G-N, not the sine and cosine type of sign, but the sign. And we need to have this because it's important in terms of getting a quantities, very specific quantities. So our sign convention is such that positive work, okay, is equal to work done on system. And this is very important So positive work is equal to work done on our system, and negative work, we know work is a scalar, so it can have a sign, S-I-G-N. It can be positive or negative. And so that's what I'm addressing now. So a negative sign associated with W, or work, is going to indicate work done by the system. Okay? And let me qualify this a little bit further. This is positive work is work done on the system by surroundings. Okay, and that makes sense because that external pressure is the surroundings. It's coming somewhere from the surroundings. So the surroundings did work on our system. Okay, and likewise, negative work is work done by the system on the surroundings. Okay, I think it's quite, for you all, it's going to be rather simplistic. These are very simple terms. Okay, so in order for this to hold, okay, we will now have to make this minor modification to our expression for work. For the differential amount of work, dW is going to have a negative sign in front of it, P external times dV. And this is something that we will use over and over in our discussion of the first law and work for this course. Okay, so dW is minus P external dV. So of course you don't have to memorize anything, but this is something that you'll see over and over again that you'll just memorize it. Okay. So some things I want you to keep in mind. Keep in mind when dealing with work, one, don't forget the line. And what I mean by that is this guy. Okay, don't forget that. All right. Two, don't forget the negative sign. Okay. And three, don't forget, forget external pressure. Okay, so this is the most general form of the work that we're going to use in this course. So let me just, and this is the most general form of dW for this course. Okay, so some important things here to keep in mind. Okay, great. Any questions? I'm going to move on. Okay, we saw that dW is less than 0, negative, if system does work on surroundings. Okay. Actually, let's go back and have this be positive. Sorry about that. If system has work, sorry about that, folks, has work done on it. By surroundings. And so we see here in our piston assembly that we have used as our example, and this is why I wanted to change it to positive. Okay, so we had initially our gas, which is our system, and we have our P external. Okay, and this is our gas, which is our system, which is at volume V1, temperature T1, pressure P1. And of course we have N. We go through a process. there's some process that the system undergoes, okay? And at the end of the day, our volume is now here, let's say. We have P external. Here's our piston head. And now we have V2, T2, P2, and of course, N doesn't change. We see here that V2 is less than V1, right? I think that's obvious. So we can say that for a differential change in this process, since V2 is always going to be less than V1, those are the two final states, dV is going to be less than 0. Okay, if there's any disagreement, please let me know, but I think dV is always, as you're compressing, as the process unfolds, and the process is this compression of the gas, at any instant of time during this compression, dV will always be less than 0. Volume is decreasing, so the future volume will be less than the current volume, and since dV is just future minus current, dV is less than 0. Okay, so if we look back at our expression for dW, which is minus P external times dV, we find, and of course pressure is going to be positive. We have a positive pressure acting on this system, so this is positive. dV for this whole process is negative throughout the process, so this is minus. So what we find is that a positive times a negative gives us a negative, and then we multiply it by this negative to give us something that is greater than 0. So in this case, dW is greater than 0. Okay, and over the process then, the total work will be greater than 0. And that's because the surroundings, as represented by this source of external pressure, has done work on the system to compress it. Okay, and so that's how this negative sign takes into account our sign convention. Okay, and so that goes back to this idea of our sign convention, where positive work is work done on the system by the surroundings, and negative work is the work done by the system on the surroundings. Okay, any questions on that? Any questions at all? Okay, I think it's fairly straightforward, and I'm taking some time so that everything is clear to everyone. I don't want to rush through this because it's so important. Okay, awesome. So now let's see what this line means. Okay, I've been very stubborn about having this line along. So let's do some examples, or maybe a very simple example in the remaining time that will illuminate 2 points at least about work. Okay. Okay. So let's see. How shall we do this? Let's go back to dW is equal to minus P external times dV. And it seems that work is a function of pressure and volume. Because on the right-hand side of this expression, I see pressure and volume. So perhaps we can sort of visualize this. Visualize work on a graph. Okay. And on this graph, on one axis, we would have P external in whatever units are relevant or associated with pressure. And on this axis, we would have volume, again, in whatever units one wants to work with. Okay. And so let's take a look at a process. Okay. And this process, I'm going to, again, make it a very general process, but it's going to illuminate a few things. So we're going to start here, and we see that on our pressure volume diagram that we have some initial pressure P1 here and some initial volume V1. Okay. And then what we'll do is go to a state here where the volume is P2. Sorry, the pressure is P2. My apologies. It's a vertical transition, so think about it here. We have a P2 here, but the volume doesn't change. Okay, so that's state 2. So let me label this as P2, and this guy is going to be P1. Okay, and you can see that P1 is associated here, P2 is associated here, and of course this will be V1. So over here we'll write V1. Then what happens is our system is taken to this point here, where we still have P2, but now we're at V2. So this point is at P2, V2. Okay, and then finally we come down here, where we're at P1, V2. Okay, and so what we're going to do is going to follow a path. This is our initial point, right here. Our initial equilibrium state. Okay, and we're going to follow a path that goes this way, then this way. Whoops, these are straight lines, by the way. Okay, so these are straight lines. And then this way. And then finally, this way. Okay. All right, so that's our process. So we're going to start here at our initial state. And let me label that initial state as 1. This is 2. This is 3. This is 4. Okay. And so that way we don't have any confusion. And what we want to look at is the work associated with some of these processes or some of these legs of our process. So is everyone clear? This is a way to visualize our system, and that system, again, now it can be some generalized system, an abstract system. It starts at this point, which is an equilibrium state, where you have P1, V1, and of course T1, I haven't written T1 down, or the temperatures, but of course there's a temperature. N is not going to change, so this would be a closed system. Delta N is 0 for the whole change here. And that system is going to go from this combination of pressure volume to this combination, and then this combination, and this combination, and then back. Okay? So let's first consider some values of the work associated with this process. And so let's say, let's consider the work involved for this stage. Okay, so to go from 1 to 2. Okay, so work involved to go from 1 to 2. Okay, so that's this process right here, from our initial state 1 to this other state 2. Again, all our equilibrium states. And the way we do it, so this is an example of how we would sort of attack a problem that asks us to calculate the work. Okay, so the problem in very general terms would be, what is the work? What is the work? And there might be some other words to give you further description. But this is the general type of problem that you want to be looking for. And so if you're asked, what is the work for some process? Well, the first thing we do is go to our handy and trustworthy expression. EW is P external times dV. Okay, we can never go wrong if we start with that. Okay, so now we just have to fill in things here. Okay, so for the process from P1 to from state 1 to state 2, we see that the pressure is changing, right, from P1 to P2. So we might be looking or thinking about, well, what is P external? Okay, so we'll hold on to that. We'll hold on to that. We look at dV now. And what can you say about dV? It's kind of obvious, right, for this process? dV is going to, Exactly. dv is 0. And so these are the easiest, and it's always nice to see these questions where dv is 0, because you know then that dw must be 0. Okay? And so now if I wanted to find w for this process, this is the differential form. This is the differential amount. I'm going to be totally rigorous here. Okay, this is the differential amount. So the total work okay, W, sorry about that. So the W to go from 1 to 2 is going to equal the integral, because this guy is a differential. Okay, so it's going to equal the integral to go from equilibrium state 1 to equilibrium state 2. And now I know you're used to having limits here, but in this course we're going to again use different ways of looking at integrals. Okay, so what this is telling me is that to get the total work, right, this is not a differential, this is the total. To go from 1 to 2, I have to take the integral of something that's a differential. That's all this is saying. And I have to take the integral of this differential amount from state 1 to state 2. So this is what we're saying is I take the integral of dw from state 1 to state 2. I'm using mathematical symbols to represent what I just said in words. So this construct, this thing here, okay, is the mathematical way to represent these words. Taking the integral of dw from equilibrium state 1 to equilibrium state 2. That's what this is. It's a mathematical representation of words. So I've taken one language, English, and I've translated it into the language of mathematical symbols, or using mathematical symbols. That's all that is. Okay? But we know now we have a relationship for dw in terms of other things. So we can now further refine this expression. And we know from this guy here, dw, okay? So we go from equilibrium state 1 to equilibrium state 2 is minus P external dV, okay? But wait a second, once we get to this point, we see that, okay, there's something here. This is called the integrand. This is called the integrand, just to refresh your memory from calculus. That's called the integrand. And this guy is this differential change in the variable on which our function depends. And so remember, I just mentioned that work appears to be a function of external pressure and volume. And when we represent the total work in terms of an integral, we see that volume appears as a variable. So work is related to volume in this case. So we can write the work to go from equilibrium state 1 to equilibrium state 2 as this integral using this guy is minus P external dV. But since work is going to depend on volume, we can write V1 to V2, where V1 and V2 are the volumes that correspond to our initial and final states. Okay, so this is our initial state, and this is the volume in the final state. Okay, but we know that V1 is equal to V2. So what we could have done is just say, all right, well, we can let this be V1 and V1, or V2 and V2. And this is equivalent to V2, V2 minus P external dV. And what are these integrals? If we have the same limits on an integral, perhaps you remember from calculus, the integral has to be zero. Okay? And so I went through this very, very explicitly just to show you that for 1 to 2, And of course, there will be units of work. What are units typically of work? Any unit. You can name any unit for work.
Joules.
Joules. Fine, that's great. And that's abbreviated J, right? So this is 0 joule. And that we could have seen just from the graph, okay, and thinking about it. But in this case, we went through this explicitly because we're going to do this again for the other stages from 2 to 3, 3 to 4, and back to 4 to 1. Okay, so go over these again on your own. Very, very simple. I think you'll agree. It's nothing hard at all. It's actually very simple. I think you're all very capable of this. Okay, thank you all for your attention. I will continue analyzing this process next class. So we're going to look at this leg and this leg and this leg and some other things. And there'll be some very cool insights that we will glean from this analysis. Any questions before I end the meeting? There will be the discussion sessions at 11:30 today, and then 5 to 6 in the evening. So I highly encourage and invite you to at least attend them. And every resource we have, just take advantage of it and make use of it so you can rock this course and bust it and do well in it. Okay, and of course I'm available via email to chat if you need to. Okay, and I posted those extra resources on the Canvas website. Please take a look at those. And so I think if you just keep exposing yourself to those things, everything will fall into place. Okay, thank you all for your attention. And I'm going to end the meeting at this point. Okay?
Thank you. Have a nice day.
Thanks. You all have a nice day too. Be well.
Thank you.
Thank you.
Thank you.
Bye.